What is the motion of atoms and electrons at absolute temperature? At absolute zero temperature, atoms and electrons are in a state of minimum thermal energy and are almost static. At this temperature, atomic vibrations are almost non-existent and electrons exist at energy levels close to their ground state. Then, as the temperature rises, the atoms vibrate more actively and the electrons move? That's right. As the temperature increases, atomic vibrations become more active and electrons move to higher energy levels and begin to move. At high temperatures, the interactions between molecules or atoms become stronger, which can change the structure and properties of the material. These movements and energy changes affect thermodynamics and changes in the state of matter. Then, if the volume increases when the temperature rises, if the pressure is increased at this time, the motion of the atoms will be reduced? It is a common situation that the volume increases as the temperature rises, but increasing pressure does not have a specific effect on reducing the movement of atoms. When pressure increases, the interactions between atoms or molecules become stronger and the density of the material can increase. However, as the temperature rises, the thermal energy of atoms increases and their movement becomes more active. Therefore, even if the pressure is increased as the temperature rises, the movement of atoms is not reduced. Then, what kind of superconductivity occurs when the pressure is increased at a high temperature for a material? The phenomenon of superconductivity that occurs when pressure is increased at high temperatures is known as high-temperature superconductivity or high-temperature superconductor. This phenomenon means that the superconductivity phenomenon that was generally observed only at low temperatures is also observed at a certain temperature or higher. Yttrium Barium Copper Oxide, and bismuth strontium calcium copper oxide, are compounds that are representative high-temperature superconducting materials with tin and copper as their main components. These materials show the superconducting effect that was previously observed only at very low temperatures, even at relatively high temperatures, which is evaluated as a revolutionary discovery that allows the observation of the superconducting phenomenon at relatively high temperatures. Then, what is the mechanism for this high-temperature superconductivity phenomenon? The exact mechanism of high-temperature superconductivity has not yet been fully elucidated, but several hypotheses have been proposed through theoretical studies and experiments. One major hypothesis is based on the concept of Fermi liquid. Fermi liquid describes the phenomenon in which electrons interact with each other at a specific energy level. In high-temperature superconducting materials, electrons are combined in a special way due to strong interactions between these Fermi liquids, creating conditions where the interaction between electrons is weakened. Another hypothesis is based on the concept of magnetic interference, which explains the influence of the interaction between magnetic fields and electrons in high-temperature superconducting materials. This hypothesis suggests that the complex interaction between magnetic fields and electrons induces the superconducting phenomenon. However, since the exact mechanism of high-temperature superconductivity has not yet been fully elucidated, more research and experimentation are needed.